book in chapter 2, I think it was example 1, does the contour integral of a Gaussian. And so I need that fact for two purposes. One purpose is for the uncertainty principle. So we have this wonderful result that the product of these variances has to be at least as large as a universal constant. So the question becomes, well, does it have to be that small? Or maybe does it have to be a little bit larger than that? Is it possible to attain this minimal bound? And the answer is yes, it's possible to attain. And if you have any deductive powers, you should be able to figure out what function leads to attaining that.
Gaussian.
The Gaussian, right. And so the Gaussian actually gives you minimal. And then you can go back and you can see, where did we do approximations? Where did we have inequalities enter the argument? It was the Cauchy-Schwarz lemma. So the question becomes, when is the Cauchy-Schwarz inequality an equality? All right. So the Fourier transform of a Gaussian. So there are lots of ways to do this calculation. What I'm going to do is I'm going to go back to not the notation we've been using for the physics uncertainty principle. I'm going to go back to having my 2 pi's. I like my 2 pi's. Alright, so let's say f of x is e to the negative ax squared for some a. And I want to calculate its Fourier transform. So I want f hat of y is e minus infinity to infinity, e to the negative ax squared, e to the minus 2 pi I xy dx. This is technically not a Gaussian unless A happens to have a particularly nice, well, in fact, even then I don't think it's going to work. It's not going to integrate to 1. That's fine. You can always put in the normalization factor to make this a probability distribution. I just care, how does the function e to the minus ax squared transform? And up to a constant, it's going to look like e to the minus ax squared again. So the question is, what's the best contour to use for something like this? So we haven't done contour integration in a while, so this is one of the reasons why I like using this as a way to segue back into number theory and back into stuff you've done earlier in the semester. I want to have the integral of e to the minus ax squared. I know that. So we know the integral from minus infinity to infinity of e to the minus ax squared dx. This is the square root of the integral from minus infinity to infinity, e to the minus a x squared plus y squared dx dy. I'm just reviewing an old polar trick. I'm basically just squaring the integral and taking the square root. The reason I do this is I can now use polar variables. Integrate r goes from 0 to infinity, integral theta goes from 0 to 2 pi, e to the minus a r squared r dr d theta. The theta integral is going to just give me a 2 pi. For the r integral, I need to have an a and I need to have a 2. So I then have to multiply by 1 over 2a. And now when I do the integral, I'll have e to the minus ar squared 2ar dr. That's going to integrate to 1. And so if I've done all the algebra correctly, and if not, I don't really care, it's just the square root of pi over a. And just some nice constant. Okay. And then as a quick check, if a equals 1/2, then this would be the square root of 2 pi, which is exactly the normalization constant I need for the Gaussian. Okay, so we haven't done any algebra mistakes. So there are lots of different ways of calculating the integral of e to the minus ax squared. It's a real integral. If you know the gamma function, you can convert it to a gamma function problem. And then there are techniques to evaluate this. It's really gamma of 1/2. We're going to assume that this is known. And now we want to figure out, what is the Fourier transform? So somehow my contour should include the real line. Because if I take the real line, if I don't have this part over here, I'm in good shape. So the question is, what function do I want to consider? What contour do I want to take? Any thoughts on what function I should look at? So this is the hardest part of the problem. Okay, so for the contour I want a rectangle. What function do I want? Because that's going to affect if I want rectangle up, rectangle down, thin rectangle, fat rectangle. What function do I want? And remember, it's got to reduce to something that I can understand. So I've got to convert something to a function of z. What do I want to convert to a function of z? We don't have that many choices. We've got either this or this.
Well, since we understand the first one,
We understand the first one.
we should probably do the second one.
So
Or should we do that one because we understand it?
I would much rather do things I can do.
Okay.
So I understand the first function. Let's convert the first function. So let's take f of z to be e to the minus a z squared. When z is real, when z is real number x, this is just e to the minus ax squared. We know how to do that. So I probably want to go from maybe like minus r to r. And I can understand that function. Now the question is, do I want to go up or do I want to go down?
We have decay and z is positive. Oh, we did both directions.
So let's say z equals x plus iy.
So we get a minus.
Then f of x plus iy is e to the minus a x plus iy squared. E to the minus a x squared. E to the minus 2ai xy. And then the I squared becomes a minus 1 times a becomes e to the a y squared.
But,
What?
I mean, if you change, you have two different terms that go in the opposite direction depending on when y grows. Although it seems like it,
Yes.
This works, doesn't it? Because we have decay if y is. Well, if you do it the other way, if you do x minus iy, then you're going to end up with a positive term in the middle.
So no matter
this seems better, yeah.
so no matter what, we're not going to get decay in y.
Yeah.
We're screwed.
So take a short rectangle.
Take a short rectangle. Don't go for decay in y because you're not going to get it.
so do you think like take like a rectangle and expand?
Yeah, so we either want to go up or down just a little bit. And notice, if we just go up and down a little bit, when we go along the top or the bottom, e to the a y squared will be constant, will just come out of the integral. And doesn't this look like the factor we need for the Fourier transform? We want to have e to the negative 2 pi I xy. We have e to the negative 2 ai xy. So we don't want to evaluate it at x plus iy. We want to evaluate it at x plus iy times what? Times pi over a. So I want to put in a pi over a here. And now when I put in a pi over a, that becomes a 2 pi. And over here, when I put in a pi over a, I'll get, I think, pi squared y squared over a. And now it's set up beautifully for the Fourier transform. So what this is telling us is if we can calculate some of these things on the real line, we can calculate them wherever we want. Do we want our rectangle going up or going down? Up. I don't think it really makes much of a difference, but I prefer going up when I have a choice. I've already got the minus 2 pi, everything looks good. And so, if this is r and this is minus r, this would be r plus I y pi divided by a. And now, bottom is going to be an integral I know how to do. The top is going to be the integral I want multiplied by something that doesn't depend on x. So all that's left is the two vertical sides. Well, on the two vertical sides, I'm going to be running from r plus I0 to, oh, sorry, I should put pi y over here. Pi over here. So on the vertical side, I'm going to go from x plus I times 0 to, I'm sorry, from r plus I times 0 to r plus Iy pi over a. So on these vertical sides, the imaginary part is going to be at most y pi over a. So as big as this is going to be, x is going to be of size r, and r is going to go to infinity. I'm going to have an e to the minus ar squared. That's going to dwarf this. So the two vertical sides don't matter in the limit. Unless, of course, we were idiots and we chose a to be negative. Okay? But we wouldn't do that to ourselves, right? Why would we not choose a to be negative?
The integral wouldn't converge.
Yeah, the integral wouldn't converge, right? If I take a to be negative, I'm integrating a growing exponential. Not going to happen, okay? So a is going to be a positive number. So the two vertical sides don't matter. Vertical sides, negligible, bounded by e to the minus ar squared times e to the pi squared y squared over a times y pi over a. This is not the best bound. I'm getting this bound by saying, well, what's the length of the vertical side and what's the maximum value of the function? This is overkill, right? Does the function always take on its maximum value?
No.
No. I could, integrate this and try to find a better approximation. Is it worth trying to find a better approximation? No, I'm going to be sending the contour off to infinity. This term is going to go to 0. There is no point in doing more work here. And as there's no point in doing more work there, we will not do any more work there. Right? It's not going to help us at all. This is perfectly fine. This has rapid decay. Alright, so it's been a long time since we've done a contour integral. What does Cauchy's theorem tell us? So, I don't, do you want me to pick or not? I feel like Vanna White. What do you, yes?
Where did the middle term go in your bound?
What's the absolute value of the middle term? 1.
Yeah.
That's right, 1. So what does Cauchy's formula tell us? We have a contour, we're integrating. What does Cauchy tell us?
It'll integrate to 0.
It'll integrate to 0. Why 0?
Because it doesn't have any poles.
It doesn't have any poles. Right? Beautiful! The integral we know is related to the integral we want to find. And there's no there's no residues to calculate. So we get the closed integral of f of z dz equals 0. Notice we're traversing this in the wrong direction. Well, since this plus this equals 0, bringing this over to the other side now restores its orientation. And so we get the integral from minus infinity to infinity of e to the minus ax squared dx is equal to the integral from minus infinity to infinity of e to the minus ax squared, e to the minus 2 pi I xy, e to the pi squared y squared over a dx. Well, this integral here is just the square root of pi over a. We bring this exponential to the other side because it has no dependence in the integration. E to the pi y squared over a, and that's equal to integral from minus infinity to infinity of e to the minus a x squared, e to the minus 2 pi I xy.
You mean the extra negative?
Yeah, just square.
Probably, did I drop something?
Should be
Yes, this becomes negative when we bring it over, thank you.
Why did pi instead of this pi?
This pi squared, pi just dropped the pi squared, I just dropped the pi squared.
Are we, but I thought we were trying to evaluate what the left-hand side was.
Which, this?
Yeah.
No, we know this. Right.
So what do we?
We're trying to evaluate the Fourier transform of it, of e to the minus ax squared. So we know the Fourier transform when y equals 0. When y equals 0, this is just the normalization factor of the Gaussian. And if you know the gamma function, I believe it's just gamma essentially at 1/2 modulo some rescaling of variables, some change of variable formula. But this is the Fourier transform. So we get f hat of y is square root of pi over a, okay, some normalization factor, e to the minus pi squared y squared over a. So the interesting thing to note is we start off with e to the minus ax squared, and we end with e to the minus something times y squared. So it's still a Gaussian. The interesting fact is the a starts off in the numerator and then ends in the denominator. So if a is a very small number, if a is like 1 over n, then this integral is then e to the minus ax squared is hard to evaluate. So let me do this very carefully. So let's say a equals 1 over n, n is big. If you have e to the minus ax squared, you need x to be about how big do you have to really worry about x? Square root of n. To cover yourself, you normally do maybe square root of n log n. Go a little bit further just to be safe. Okay. I just realized I don't think I turned out. Yes, somebody had called me. Would have been Munchkins. I forgot to turn off my phone. Yes, could have been a Munchkin day. So here, the number of terms I need is about square root of n. What about e to the negative pi squared y squared over a? We need y about how large? Well, since a is 1 over n,
Square root of pi squared n.
yeah, about 1 over square root of n. So remember, we have Poisson summation, which says the sum of f of n is the sum of f hat of n. So over here, if I have a sum of something like this, I'm going to need about square root of n terms. How many terms am I going to need here?
1 over square root of n.
Okay, and since I have to have an integer number of terms, how many terms will I need? 1 term. That is an outstanding trade, right? Essentially, if you want to evaluate this function, just do 1 term. Okay.
What does it mean that we need x to be about?
Well, if I look at the argument of this,
Okay.
as long as x is less than square root of n, ax squared is going to be a number that's very close to 0.
Okay.
So all of those numbers will evaluate to essentially 1.
Then there will be-
So in terms of how many terms I have to keep track of,
Okay.
I'm going to have to keep track of roughly square root of n terms.
Okay.
It's not until x breaks square root of n that I start to see any decay here.
So then why, in the second one, do we only need y to be about 1 over square root of n and not 1 over square root of n, log n over 1 over square root of n?
You could play those games as well.
I guess it's like you didn't go the further step in that part. It's like optional.
We can definitely put in the log in as well, but yes.
Okay.
Wait, don't you want to
And I don't care if it's square root of log or log, but it's going to be something small. Right, so the whole point of Poisson summation is take a slowly converging sum and replace it with a rapidly converging sum. And typically rapidly converging means just 1 term matters. Okay, so this is the power of Poisson summation. Okay, any questions on the Fourier transform of the Gaussian? Okay, so what we're going to do now is we're going to revisit number theory. And so I promised you that we would get to the analytic continuation of the Riemann zeta function. So there's a lot of different ways to do this. I'm going to go through one of the standard proofs using, so this is analytic continuation of zeta of s. So I'm going to define theta of t to be the sum, and it goes from minus infinity to infinity, e to the negative, I think it's pi n squared. There's lots of different ways, okay. And we're going to use the letter u because the book likes to use u. Pi n squared u. So I am going to treat you like what today? Graduate students. So what that means is I'm going to do very little algebra. My goal is to describe to you the steps you need to do, and then you can do the algebra if you want to see the algebra. Okay? The algebra is in the book, I think it's page 168, in the analytic continuation of the Riemann zeta function. So the very first thing you should ask is, when you see this function, does this function make sense, and if so, where? So for what values does this function make sense? Okay, good, not zero.
I'm sorry, just as a point of, they use t in the book.
They use t, but then they switch to u later.
Never mind.
Yeah. So when they invoke transformation properties of theta, they use the letter u. I don't know why they go from t to u. I scratched off the t's in my notes. So when u equals 0, we have trouble. Where else do we have trouble?
U less than 0.
I'm sorry?
U less than
U less than 0. So we need u to be greater than 0. So as long as u is greater than 0, everything is fine. Does it converge rapidly or slowly? So one way to look at this factor is e to the negative pi u to the n. Well, it'll be less than or equal to that. So I can bound it with a geometric series. So I can bound with a geometric series. And of course, it's much better than that, because I don't just have e to the minus pi u n, I have e to the minus pi u n squared. So this is going to decay very rapidly. Right? If I take just one term, alright, I've got n equals 0, I get 1. The next terms will then be e to the minus pi times u, then e to the minus 4 pi times u, then e to the minus 9 pi times u. So the terms, their contribution is getting smaller and smaller and smaller. So using Poisson summation, theta, and I just want to save time and just write what it is. Theta of u is u to the minus 1/2 theta of 1 divided by u. And again, this is exactly set up to use Poisson summation. So I take f of x to be e to the negative pi u x squared. So what we're doing is we're just taking a to be pi times u in what we did before. And now when I sum f of n, that's going to be this sum. F hat of y, well, we just showed that it's going to be square root of pi over a. So square root of pi over a, the pi's cancel, and we have a square root of u down below. So we get a u to the minus 1/2. And now we get e to the negative pi squared y squared over a. So pi squared over a, pi squared, one of the pi's cancels, we'll get negative pi y squared divided by u. And so now you see f hat of n is just going to be u to the minus a half e to the negative pi n squared over u. This is essentially evaluating our function not at u but at 1 over u. So this is the proof of this relation. It's a consequence of Poisson summation. And of course, if u is greater than 0, 1 over u is also greater than 0. Alright, so now I can erase all the Poisson summation stuff. It served its purpose. I can erase the Fourier transform of the Gaussian. It served its purpose. It allowed us to have this nice relationship between the two. Alright, it turns out it's technically a little bit more convenient not to consider theta, but to consider an extremely close cousin of theta. And so we let c of u be theta of u minus a half, I believe. Yep, minus 1 over 2. So can someone tell me why this might be a good thing to look at? The hint is it gets rid of some discrimination.
Around 0?
Yeah. What being 0? There's a lot of variables today.
Oh, yeah. Like,
There's an asymmetry in theta.
and from like 2 infinity?
Yeah, normally I like to have sums from 1 to infinity or 0 to infinity. I have a sum from minus infinity to infinity. Well, when I have n squared, 5 and negative 5 have the same contribution. 4 and negative 4 have the same contribution. But 0 is only counted once. So to get rid of the fact that 0 is only counted once, let's throw it away. And now everything that remains is counted the same number of times. Alright, and so now, when you just do the algebra, this is equal to u to the minus a half c of 1 over u plus 1 over 2 square roots of u minus 1/2. So do you think this is hard to prove or easy to prove? Easy. We know how theta transforms, right? So just shove in, 1 over u, and then just do the algebra. So this is just algebra. Okay, nothing deep here. But not surprisingly, if theta transforms nicely, c transforms nicely. So it turns out in number theory, when we have analytic continuations for the Riemann zeta function and other things, you always want to ask, what is the source of that continuation? What allows us to extend it to other values? And here, it's basically the transformation properties of the theta function. And you can consider more general functions which are built from functions that have nice transform properties. And those symmetries give you extensions. So I do apologize, but as my advisor says, until you prove the Riemann hypothesis, thou shalt use Riemann's notation. So this means we have to use c for the completed Riemann zeta function. We also have to do the annoying thing when we do complex variables for the Riemann zeta function. We write s as sigma plus it. Why is this bad notation?
It mixes Greek and...
Yeah, it mixes Greek and non-Greek.
Who does that?
Right. Riemann did it. Thou shalt follow Riemann. Okay? Until you prove the Riemann hypothesis or disprove it, we will use his notation. Sigma plus it.
Are these commandments written down
Yes.
somewhere?
Yes. But you have to have a PhD before you're allowed to see the book. Okay. Thou shalt use sigma plus it. I agree it's strange, but... So this is the completed Riemann zeta function. If you've never seen this before, when you put a colon sign before an equal, that means it's a definition. Alright. Pi to the minus s halves, gamma of s halves, zeta of s. Alright. That is the completed Riemann zeta function. It turns out this is equal to, and this is a big theorem, the Riemann zeta function at 1 minus s. And this allows us to analytically continue the Riemann zeta function. If we know its values, as long as the real part of s is greater than a half, well then if we look at 1 minus s, the real part will be less than a half. And so if we know the Riemann zeta function in one region, we actually get it in another region. We understand pi to the minus s halves, that's trivial. Gamma function's a little bit more involved, but we understand that. And then we actually already proved how to analytically continue the zeta function to the real part of s greater than 0. So we actually already have enough now, once we have this fact, to know the Riemann zeta function everywhere. This does not mean that zeta of -1, zeta of 0. So if I put in s equals 0, I get zeta of 1 is essentially the same as zeta of 0. What would the Riemann zeta function at 0 be? Or the Riemann zeta function at 1? So the zeta function is the sum of 1 over n to the s. So either 1 plus a half plus a third plus a fourth, or 1 plus 1 plus 1 plus 1, depending on which point you want to evaluate it. Just because I have a continuation doesn't mean that it's the value of the series of those points. Those series don't make sense. But there's ways to generalize the function to make sense, and in some sense to interpret what that means. So if you ask a good physicist what 1 plus 2 plus 3 plus 4 plus 5 plus ... equals, they would say -1/12. So the sum of the positive integers is -1/12. You also have to remember the gamma function actually has places where it blows up. And that can compensate for places where the 0 has issues. So lots of wonderful stuff going on. All I wanted you today is give you an idea of the inlet continuation of the Riemann zeta function. So the first thing is, this is equal to, so scribble of s is the sum, n goes from 1 to infinity, of pi to the minus s halves, gamma of s halves, n to the negative s. Okay. So far so good? What can we do now? We don't have that many options.
You can pull out everything that doesn't have to do with n.
We could pull out everything that doesn't have to do with n, but then we just get back to the Riemann zeta function.
Yeah,
So the whole thing is we've expanded the Riemann zeta function. Alright, so we pull out everything that has to do with n and we come back to here.
and then we do it again.
And then we do it again and we come back
Okay,
here.
good, now we're set.
Now we're set, okay. No, but you try it, see, does it work, does it help? It doesn't help. So we need something else. What else can we do? There's two things, one works, one doesn't.
Take a Fourier transform of that?
Not a Fourier transform. I'm beginning to wonder if I actually covered this function in this class. Did we cover the gamma function in this class? Oh, okay, if we haven't covered the gamma function, then this will be a harder question. So the gamma function is a generalization of the factorial function. We have an integral representation of the gamma function. Oh, we haven't done gamma in this class? Okay, digression. So far this class has changed. So we'll do the gamma function today and then we'll come back and finish this on Friday. So gamma of s is defined as the integral from 0 to infinity of x to the s minus 1 e to the negative x dx. And an equivalent way of writing it is it's the integral from 0 to infinity e to the minus x, x to the s over times dx over x. And the question is, why would you care to write it in these different ways? Well, dx over x has a really nice interpretation. If you've seen Haar measure, if I change x by multiplying by 5, dx over x is invariant. It rescales nicely. This is a really good measure to have on 0 infinity. And this is essentially a Mellin transform of the exponential function. So if you had to evaluate this at a choice of s, what value of s would you choose? 1. So the first question is always, which values of s does this make sense? Well, I have great decay at infinity. So it doesn't really matter what s is. This will be at most polynomial growth, exponential decay beats polynomial growth. Everything is fine at infinity. The difficulty is at the origin. As x gets closer and closer to 0, e to the minus x looks like 1. Okay, so I need x to the s minus 1 to be integrable. What do I need to be true about s?
Greater than or equal to 1.
do better than that. If x equals 1, okay, then I've got no x term at all. But I can integrate x to the minus a half near the origin.
Greater than or equal to 0.
Greater than or equal to 0. Back up just a little bit.
Or greater than 0.
Greater than 0. So you're okay if the real part of s is greater than 0. All that matters in terms of the magnitude is the real part. If the real part is greater than 0, you're fine. Alright, so gamma of 1 is going to be the integral from 0 to infinity, e to the minus x dx. One of the most pleasant integrals to evaluate. What will you get? The students who were in my probability class last year are expecting a little faster answers, because I know you guys have seen this.
Oh.
I was checking
Yes. There you go. What if I did gamma of 2? Then I'd be integrating from 0 to infinity of x e to the minus x dx. How do I do this?
Integration by part.
Integration by parts. And when the dust settles, you get 1.
What's the expected value?
Which is
Another way of looking at this is it is the expected value, and there's a great connection between moments and expected values. So, gamma of 1 is 1, gamma of 2 is 1, therefore gamma of 3 is also
2.
2, yes. Okay, so it's the Fibonacci's. It's 1, 1, 2, 3.
N minus 1
factorial.
N minus 1 factorial.
It would have been fascinating if it was the Fibonacci's, but... So instead of doing the analytic continuation of the Riemann Zeta function today, we'll do the analytic continuation of the gamma function today. Okay, so gamma of s plus 1 is the integral from 0 to infinity of x to the s plus 1 minus 1 e to the minus x dx. So we integrate by parts. U is going to be x to the s, dv is e to the minus x, du is s, x to the s minus 1, dx, v is negative e to the minus x. So when I evaluate the boundary terms, x to the s, e to the negative x, it's 0 at 0, and as x goes to infinity at 0, the boundary terms vanish. The negative sign reinforces the negative sign in the integration by parts, and we get gamma of s plus 1 is going to be the integral from 0 to infinity of s, x to the s minus 1, e to the minus x dx. Alright, I just pull the s outside the integral, and then that's the definition of gamma of s. So gamma of s plus 1 is s gamma of s. So once I know the value of the gamma function in a band of length 1, I know it everywhere. And what you get is you get gamma of 1 is 1, gamma of 2 is 1, gamma of 3 is 2, gamma of 4 is 6. And so now how do we rewrite these in a more intelligent manner?
0 factorial,
Yep.
1 factorial.
0 factorial, 1 factorial, 2 factorial, 3 factorial. Gamma of n plus 1 is n factorial, n greater than or equal to 0.
And integer. Well, yeah.
Okay?
Don't you want to ensure that n is a natural number? Too?
Yeah, it's an integer.
Oh.
So, when you look at this, what makes you weep in terms of notation? If you could have 5 minutes alone with the person who created this definition, what would you ask them?
why is the negative 1?
I'm sorry?
Why is the negative 1 in the definition?
Yeah, why is the negative 1 in the definition? So I tried to justify it by saying we have the negative 1, so we have dx over x. That transforms nicely. But at the end of the day, we get gamma of n plus 1 is n factorial. It's shifted 1 from the factorial function. Why would you do this to yourself? Right? We've seen this issue, and I know the physicists have seen this issue numerous times. You have multiple choices of normalization. Which normalization is going to be best? And unfortunately, if we want to restore the factorial function, this is not good. It's going to shift by 1. But it's convenient for a lot of other things to have the gamma function defined like this. So, a particularly nice value is gamma of 1/2. Anybody remember what that is?
Pi.
Almost. Square root of pi. So if anybody ever asks you, what is negative 1/2 factorial? You know, how many ways can you order negative 1/2 of a person when order matters? The answer is square root of pi. Okay, this application, yes. So if you could, can I see Jaja?
Ooh.
I can now charge this to my accounts. So, oh, I'm sorry, this is only half of a person. So, if you wanted to order half of a person, what would that be? So gamma of s plus 1 is s.
Square root of
Is it 3 halves?
No, it's.
So s would be 1/2. It would be 1/2.
Oh yeah.
So it'd be 1/2 times square root of pi. And that would be 1/2 factorial. So if we were only able to salvage half of Jar Jar Binks, and we wanted to know how many ways could we order it, the answer would be 1/2 square root of pi. This is the normalization constant for the standard normal, or it's related to that. All the moments of the standard normal can actually come from doing a change of variables. You replace x with u squared. And that's going to give you an appropriate power of u. You'll get all the moments of the normal. The gamma function is extremely nice. And it's going to be one of the key ingredients in getting the analytic continuation of the Riemann zeta function. So now what we do is, now that we have some knowledge of the gamma function, we can take what we have here, and we can expand the gamma function. And so, let's see how much time we have. We have 6 minutes. That might be enough time. Because I'm not doing algebra. And I will not worry about convergence. So that, I mean, not doing algebra, not worrying about convergence should definitely help a lot. So it's going to be the sum, n goes from 1 to infinity, pi to the minus s halves, n to the minus s. And now gamma of s halves would be the integral from 0 to infinity of, let's do it as u to the s halves minus 1, e to the minus u du. Okay. So now the question is, how? So of course we can.
Yeah.
Why do you even hesitate?
It's a finite sum.
0 to infinity. Pi to the minus s halves. But now the problem is interchanging the sum doesn't help us. Scratch that idea. But temporarily. So we have to use some kind of summation interchange. Anybody see how we can make things work? What function do we spend a lot of time talking about its transformation properties? Either negative ax squared, so we talked about this theta. And this theta was the sum, theta of u was the sum of e to the minus pi u squared. I'm sorry, minus pi un. And goes from minus infinity to infinity. So the problem is, of course, the danger of sometimes using the same symbol in places. I want to get some independence here. How can I get some independence in the exponential? So this is the stuff that the book does not cover. How can I get independence? I've got an e to the minus u. What could I do to get an independence? So I could multiply by n over n, but then I don't really have any independence. I could change variables. Right? I could send u, send u to n squared u. Or maybe even pi n squared u. Or if you want, maybe pi n squared t just so we don't confuse things. Right? If I do a change of variables like this, then du becomes pi n squared dt. And let's see what we get. We get the sum, and it goes from 1 to infinity, of pi to the minus s halves, n to the minus s. Alright, as u goes from 0 to infinity, t goes from 0 to infinity. U is now pi n squared t to the s halves minus 1. E to the minus u becomes e to the minus pi n squared t. And then du becomes pi n squared dt. And now you can see why we often don't have, why we don't like this minus 1, or we often write dt over t. Because that transforms nicely. This pi n squared will cancel the negative 1 with the pi n squared there. Pi to the s halves times pi to the minus s halves is?
Nice.
Nice. N squared to the s halves times n to the minus s is also nice. And now you can see why things are working out beautifully. So now we have a sum, n goes from 1 to infinity, the pi's cancel, the n's cancel, we have an integral from 0 to infinity, we have a t to the s halves minus 1, e to the minus pi n squared t, and in this pi n squared cancels the minus 1 over there, right? dt. Alright, now what do? Now we bring the summation inside. And now we move the summation to here. And what function is that?
Zeta.
No. Psi. Actually, it's like half of psi. Because we're only summing from 1 to infinity. Okay? And then the rest is just algebra from here. Okay? So if we had 5 more minutes in today's class, I would do the algebra, but this is a good place to solve. If you want, you can now follow the rest of the book's proof. The book did not explain how you get from this step to this step to this step. The idea is we expand out the gamma function. And when you expand out the gamma function and you can justify interchanging, now you have your theta function, or cousin of the theta function. You have like twice the c function. And that transforms nicely. And then when you just plug everything in, it all follows from algebra. So again, most of you are probably not going to work in analytic number theory. If you want to start here, it's perfectly fine with me. I want you to be exposed and see what is there, and see how these problems are done. Alright, we'll then prove using this the prime number theorem tomorrow in a little bit more detail than we did last time, just highlighting what's going on. This was a nice way to review contour integrals and the likes of that. Okay.